Hello, I'm recording this. This is a version of a talk I gave a couple of years ago at a lunchtime presentation about optimizing a 60 hertz rendering engine and simulation platform. But just in general, like how do you get code fast and work within a time frame like 60 hertz or 16 milliseconds a frame. It should be interesting to anybody who works in games or cares about performance. Well, let's go. Tiny bit of background on me. My name is Kadali Pasternak. Right out of school, I worked on television commercials doing special effects. Then I worked on massively multiplayer online role-playing game. I spent 11 years at Boston Dynamics and 8 years at Mach Technology working on pretty much video game tech for the military, including a product called DI Guy. I also contributed to a rendering engine called VR Vantage, which was built on top of OpenScene Graph. I worked on the character infrastructure, the rendering, the shadows, the particle systems, and just generally trying to keep the product running quickly. So it's really important when you're building these kind of simulations or game engines that you understand your problem. Your problem is that you have 16 milliseconds or even less to present a frame to the end user. If you're doing VR, you have even less time. Some games are locked at 30 hertz instead, and actually that leaves you a lot more breathing room. Very often if I'm building systems that have to do stuff every frame, I think of it as having like a 2 millisecond budget. But part of what you need to think about is budgeting. Can I split up this work in a way that it doesn't take too long because I can't blow a frame? And so, you have to do a lot of measuring and, occasionally cutting. So at one point, you had profilers that just really were more about single-threaded performance. And in the last 5-10 years, flame graphs have become very common, and there's a whole bunch of nice multi-thread profilers. And one of the really important things about building multi-threaded code and trying to understand the performance is that you really want a visualization of it. In general, you want a map, especially as you have more and more complex systems, and usually you're an engineer who doesn't know everything that's going on, and it's hard to actually get a handle on when things happen in one of these engines if you're just dropping breakpoints and stepping through code. So one of the systems, and there's a whole bunch of them, that can provide a flame graph like you see below can be really handy. It really helps to sort of get a mental model around how long things take, when do they happen, are they happening on the main thread, are they happening in background threads, is something happening in parallel. So I really recommend the first thing you do actually is start making sure you have the tools to visualize and understand what's actually happening, because unlike Leet Code problems, usually big O isn't necessarily so important in these cases. It's how well you're using the entire CPU. So some of these systems, there's a Visual Studio plugin called Concurrency Visualizer made by Microsoft. It doesn't get a lot of support, but it's what I started with. I then wound up integrating Tracy, but Optic is also very similar. Superluminal is a commercial multi-thread profiler. Occasionally, it's just been handy to have in-game stats where we can just look at the values. And so the last resort for me is vTune. So I like all these tools. I found that the markers that you use for Tracy and Optic are almost interchangeable. You can actually have pound defines in a header file and switch between the two depending upon the target use case. So as I said, the Concurrency Visualizer is a plugin for most versions of Visual Studio, I think up to 2022 at this point. There was a while where they hadn't upgraded to support 2019. They're very big traces. It grabs call stacks on a regular tick on all the threads and has like deep information. So Tracy and Optic are very similar, as I said. They generate flame graphs with stacks of markers. You know, so this is what it looks like once it's connected. Let's start playback. You can actually, this is capturing the stack trace also. So we've got a whole bunch of people moving, and let's have them do something interesting. This is triggering a path plan for all the characters. And so everybody is heading to this spot. And you can see a little bit, because I'm capturing stack traces with Tracy right now, there's a little bit of a slowdown. But let's, I think we got enough data. So at the top we can see list how long each frame took. We can drill down and look for frames that were actually quite slow. In this case, I can find, all these characters. We're trying to find a navigation path at the exact same frame through our scripting engine, and so now I can see, get a sense of what was the slowest thing that is actually creating nodes inside an initial A-star path. So I've got a stack trace, and I can kind of investigate different things, beyond just what the markers specified. So it does act a little bit like a profiler, a lower level profiler in that respect, by being able to look. I can see that our path planner started over here in a separate thread, and it's doing time slicing for different searches. So each character has a certain amount of points it can search, and I can take a look and see what the most expensive functions are, and very often it is allocating data or looking at our red-black tree for the best next A-star function node to use. So that's sort of how you can start looking at this, look for hot spots, identify slow algorithms. If you don't have the markers, then you can use the stack trace information to start adding additional markers. Oh, okay, I have an area that isn't well marked. In this case, it is fairly well marked, but I can start looking at the stack trace and say, okay, somewhere in here is something that I should add a marker to get a sense for how long it takes. Each marker winds up on top of the previous call stack value. I found that Tracy had some more advanced features and runs in real time and include OpenGL and a couple other graphics API GPU tracking features, which I found really nice. And it runs simultaneously, so you can have your program running and you can watch the values and what's going on in the Tracy window. So super nice. Concurrency visualizer, you sort of have to run and then stop and then watch its data spool out. So, and then Tracy most of the time is lighter weight, but in terms of the file size, but if you run it in admin mode, it generates much larger trace files because it's also saving out the call stacks. But they are much lighter weight than the concurrency visualizer ones. We added markers that were super deep on some of our intersection testing code, and it made for pretty big files, but we didn't really notice it in terms of runtime performance. You may want to have a system like that where you can turn on and off sections of markers depending upon if it's a system you're interested in profiling at the time. So I kind of think about that at the get-go, that you probably want to be able to profile different sections at a different depth potentially. Superliminal, a whole bunch of people really like it also. I don't think it needs as much hand marking up, but I have not done a tremendous amount with it. But I think these ideas apply to all the different products here. If you run Tracy in admin mode, it adds mutex and sleep information and context migration, so that can be pretty handy. And I think it might help Optic as well. And so this is what that might look like when the process is being interrupted. It goes gray, and you can see, you know, how process is actually moving from core to core on a regular basis. Tracy lets you compare two traces, so you can see, did I improve? That says manually. Oops. Wasn't thinking about that when I did the slides. You can compare two traces, so you can see, did I actually improve this? This is sort of a statistical analysis. And so yes, in this case, it definitely got better. You know, there aren't very many outliers. But this is also nice to see. You know, if you just had an average, you can see, okay, there's a good case and a bad case. You know, this kind of lets you understand that, like, okay, a whole bunch of the time this runs fine, and a bunch of the time it doesn't. So let's think about, why is there a bimodal distribution here? vTune. vTune used to be sort of the go-to tool here. Intel made it free. It definitely has some nice, deep analysis on per CPU basis, but I always found that, like, I would see, oh, page cache misses and other faults, and I'm like, yeah, but what is actually going on here? And I'd always struggle a little bit to figure out what to do with that information. I found the last time I tried it, I couldn't get the markers support to work. And in general, I feel like vTune and even the Microsoft Profiler are good if you're trying to optimize a small chunk of code, and that's all it's running. And you're not worried about multi-threaded and asynchronous threads, which kind of add noise to that signal. So I think when if you're trying to do like a little big O analysis thing, vTune is great. And so is the Microsoft Profiler. When you're starting to have lots and lots of different systems all running potentially at the same time and caring about the frame length, I feel like these other tools are somewhat superior. So there's a whole bunch of different threading tools when you're writing C++ code. I'm fond of threaded building blocks from Intel. It has thread pools, mutexes. There's things like read-write upgradable mutex, which can be handy if you have a whole bunch of systems that are reading. You can take sort of a lightweight mutex and something has to write. It can kind of upgrade. It's definitely a usage pattern which I've seen a bunch of times, where you look for some asset, you discover it's not there, and so you're like, okay, I'm going to create this asset, and suddenly this sort of lightweight mutex can become a heavier weight one where it actually takes control. TBB has atomics and some really nice multi-threaded data structures. Some of these are also part of Boost and modern versions of C++, and I think TBB has been like removing and deprecating parts of their API over the last few years. But it is definitely a nice system for doing multi-threaded programming easily. There's also OpenMP. I have used OpenMP a few times. I find that it doesn't give a tremendous amount of control, and it kind of spawned, at least one case I saw that we were using OpenMP and multi-threaded the code that was using OpenMP, and next thing I knew, each thread had spawned off another thread pool with OpenMP. And so the contention went through the roof. So there is sort of a penalty, I think, for just thinking, I'm going to turn on OpenMP and be done. Qt also has a concurrent framework. I'm not sure how performance sensitive it is. I wound up switching to TBB over the Qt concurrent framework. There are a bunch of lockless algorithms in TBB. I would say that they are really hard to write, and you have to be pretty good at a lot of different things. So if you can find libraries that do it, you know, I would focus on those first before you try to write your own concurrent vector. Intel also put out a games task scheduler, and I think there's an EKT, I forget, there's another game focused one, and I think there's a number of game developers who prefer those lighter weight ones over TDB that gives them more control. They might have the ability to pin things to a thread, so to a specific core. Effectively, at this point, if you're using p-threads, you probably should stop and figure out one of these other frameworks. It will give you more flexibility and more tools that are cool. So what are you supposed to do with these tools? These are sort of the bullet points I think of when I'm trying to optimize code. Number one, understand your problem. Think about what's going on, when it's happening. You can try to do the thing faster. You can try to do the thing less often. You can try to do little bits of the thing. So amortizing problem over time. If you're trying to create 2,000 lights for airport runway, you're probably going to really struggle to make that fast enough to not blow a frame. So you can focus on making it a little bit faster, but you probably also want to focus on doing a time slice. Okay, I'm going to create 100 of these each frame. I'm going to put a time budget on creating the lights, and it can take 8, 9, 10 frames. People aren't going to notice that much. They will notice if you actually stop the CPU for a full, stop rendering for a full second. And then there's, can you go wide? Can you do this problem on more cores? And if you can't, maybe you can do the thing in parallel to your main thread. Do something asynchronous. Load your texture data in the background, and do your path planning in the background. You can have a whole bunch of threads that are doing things, waking up, doing some work, going back to sleep, and of course do the thing without screwing up. If you're doing something like iterating over a directory over and over and over again pointlessly and not caching the results of that, well, that's not going to help your performance. So you have to do all of this, and still use the right data structures, use the right caching mechanisms. Don't have something taking n cubed when it could be, or even n squared when it could be big O n. So some single-threaded optimizations. Caching the data, like I just said, like directory info. Data-oriented design, using smaller data structures, organized differently. There's this idea that memory bandwidth has not kept up at all with CPU CPU performance. So it may be a lot better to calculate the sign of a number rather than looking it up in a table, for instance. And there's lots of discussions by Mike Acton and a data-oriented design book, but the idea is that you want to iterate over your data in the most compact way and keep as much data you can inside cache lines. There's a nice tool called Structure Layout. Put a little image here where you can actually, it's a plugin for Visual Studio, and it lets you see how your data is laid out. And when, hey, I put in a bool, and now suddenly the pointer next to it has to be a big gap in memory. And so if you can pack your data faster, then the CPU can read it faster, and you can rearrange your data in terms of arrays of information. I found at one point I was just trying to figure out if a bunch of characters were visible or invisible, and I stored that bit in a separate array that I could iterate over, and I think I doubled or tripled the performance of just doing that. So sometimes caching that information, and if you're going to iterate over it over and over again, moving it out of a specific object and moving it into an array that will fit very tightly in memory can really help your performance. But of course, the fastest code is the code you never run. maybe you don't need to run a ray trace every frame to ground clamp a character. Maybe you can add some heuristics and move a little bit and then redo it. I remember going to GDC and they were talking about water spray and off a bow and where the ocean was for generating particle systems, and they were reusing a lot of the same intersection information. They would cache the plane of the thing that it hit and sort of bounce off of that. So you want to think, if this is an expensive operation, do I have to run it all the time? And how can I not run it all the time? And of course, like I was just saying, big O analysis, know your data structures. Do you want to do things with linear array versus a map, which is very often implemented to a red-black tree, or an unordered map, a hash table. So those all have different performance characteristics that it's important to understand, even if you can't implement them very easily. Although you should understand how to implement a linear array, and you should probably understand how a hash table works too. When you're dealing with computer graphics, there are additional spatial data structures that are pretty important. Quad trees, KD trees, oct trees, sweep and prune are all good things to look up and understand. And the quad trees and oct trees are really just a sort of a binary search in higher dimensional space. But they are the bread and butter of understanding how to deal with 3D data quickly. And of course, back to the data-oriented design, you have to know how big your data is going to be, because it may not make sense to binarily search 10 items. It might be just as fast to just walk through it linearly. And there's a reason why a lot of game developers sometimes just say use an array. I don't think that's always true, but at least for like small things, it may actually just make sense to just walk through it if it's a compact data structure, because the CPU has all of it and it's not doing any work and it's not chasing any pointers, and and maybe it's just simpler. So some other single thread optimizations to think about: pre-allocate memory. If you think that you can just push back 1,000 elements and it's not going to cost you, you're wrong. There is some geometric growth operations, but if you know how big something is, you can allocate it once. The allocating data is not free, and freeing the memory and copying it. So if you know how big something is, use that fact. Add vector reserve to your code. The STL will help, and geometric growth and smart ways of growing arrays will help, but it's not a human being. And if you understand how your code's being used, you can very often do better than they will. And sometimes also you should think about keeping around a vector potentially through multiple frames, and just so that you don't have to reallocate the memory and regrow something. Keeping around scratch data can be helpful. A lot of game developers avoided memory allocation and have custom allocators, because new and delete are not free. There's plenty of times where I've looked at code and said, oh, this is all string, doing work on strings. Why? Because doing work on strings very often news and deletes memory, all the time. So, try to keep that in mind. So in general, CPUs don't get much faster. So if that's what you've been relying on, that was good until, I don't know, 10 years ago. But gigahertz has, well, it started out megahertz. My first real computer was a Mac Plus running at 8 megahertz. A lot slower than a modern machine. But there is a limit to how hot and fast you can run CPU, and what's happened is we usually shrank and made more cores, and so you have to understand asynchronous work and multi-thread work if you want your systems to go fast. But of course, when I wrote these slides, I added SIMD instructions. You want your instructions to count, and SIMD allows you to do more work with the same, do the same work on more data at once. Single instruction, multiple data is what SIMD stands for. And there are a whole lot of intrinsics, which are specialized instructions that if you lay out your data properly, you can get a 2 to 4x speed up by using those kind of instructions. There's also an Intel language that kind of feels a little bit like a GPU shader that allows you to, write code that then gets turned into intrinsics. Because one of the problems is, you don't know what kind of CPU you're going to be running on, and if it, if the intrinsic support will be for SSE or AVX. There's a whole bunch of different instructions based upon how wide those registers, those custom registers are. And also, when you're using SIMD code, it gives a chance for the, other parts of the CPU to be well scheduled and do other work. So I mentioned earlier, I find that vTune can tell you about slow functions, but very often I'm not sure what to do with that data. And of course, their virtual functions are not as expensive as they used to be, but if you're building a very generalized system, there is usually costs to that. I found that since we had a rendering engine built on top of open scene graph, that there was just lots and lots of overhead, cache missing, just complexity that, very often it causes performance problems, walking through the scene graph, all those kind of things. Having less data compactly, figuring out where to break up your information, so that you're not doing hundreds of dynamic casts a frame, can really help your performance. And then the arrays of pointers versus arrays of objects. I think I meant structures of arrays there. Oh no, sorry. Arrays of pointers versus arrays of objects. So if you got an array filled with pointers, there's a lot of chasing. It's really easy to move things around. Sometimes you want that, especially for reordering, for certain sorting algorithms. But at the end, if the data isn't moving around that much, you will want a plain old data potentially that's just local, so you're not chasing after pointers, so that you can walk through the data very quickly. And so that's something to think about when you are designing some of your data structures. I've sometimes thought, like, okay, so for the part where I'm just doing sorting and moving things around, maybe I do want just pointers, because then I'm moving a small amount of memory around. It's easier to copy, resize, but maybe for the thing that I'm using at runtime, I want an array of objects that are just the actual data, so that it's much faster to walk through those lists and process them. So here's a couple of more examples. Do you need to update an object that's 3 miles away at 60 frames a second? Do you have to ground clamp every frame? I think Turbine's massively multiplayer engine did character physics at 10 frames a second and just interpolated previous frame to next frame. So that was one way to have a lot lower burden. Not everything needs to run at the same time step. Not everything needs to run at 60 hertz. A lot of people won't notice if you update at half that rate or a quarter of that rate, depending upon the system. Your AI system can, certainly run at a lower frame rate. So as I was talking about, the lights on an airport. So amortize over time with budgeting. Don't build systems in the first place that need to do everything at once. Always have the idea that you can run out of time and needs to be interrupted. So the lights, I just gave an example. I found that I built a system for texture streaming, for instance, where sending down the entire texture was a little expensive and would cause a stall. So instead I wound up sending like one bitmap at a time and filling in the texture. So when you build the system in the first place, you should be thinking about this. It's really important that you're not just kind of sitting there going like, okay, whatever, I'll blow a frame. If you start when you're building your code thinking about it in the first place, then it'll be a lot easier. You'll pick better data structures. You'll make better decisions, even if you don't do it initially, because you're not expecting 2,000 lights. You're expecting 100 lights or 10 lights. If you have in the back of your mind that, hey, somebody's going to throw something a lot harder at this in the future, you'll just make different decisions, and they will hopefully be better ones. So do the thing parallel to other things. Can you make something asynchronous? You know, the first answer you need to figure out is, does this have to happen this frame? And even if it does have to happen this frame, maybe you can still get away with doing something asynchronously. So if I have like 300 or 3,000 characters and I need to call them, you could start an asynchronous job. Do that at the same time as you are calling the rest of your scenario, or the rest of your scene graph, if you know how the characters are organized. And so that was something I wound up doing, blocking where I needed the result and effectively getting it for free on a separate core versus doing it inline. So, you know, if you can figure out that you can separate something out and start it at the beginning of your frame, maybe all your particle systems, for instance. I'm going to start that update at the beginning of the frame, an asynchronous job in a separate thread. You can go wide, and the code itself could be single-threaded. You just need to be willing to block when you actually need the result. And hopefully it will take less time than that. At the same time, there's asynchronous work that you don't need that frame, that you need at some point in the future. And that's things like asset loading and path planning, and you know, even merging in characters. So if I found that you know, we'd load an asset in the background and then we had to instance it. So that meant creating a skeleton for the character. VRV is the rendering engine, short for Vantage. So in the background, it made sense to actually instantiate all of the joints for the character, for the ships that we were creating in the background, because they had lots and lots of articulated parts. And then in the foreground, once that structure had all been created in the background, merge it into our scene graph. So those are kind of the things that you should think about. Can I do this asynchronously? And and how will that work when I need to merge the data in? So what happens when you now have your nice little multi-threaded system and you create too many threads, and you run out of cores? So Concurrency Visualizer will show you that somewhat clearly as preemption. Some of the other systems will as well. Effectively, you will see in Tracy that something's gone gray because it was interrupted by another thread. And so you need to start thinking about, hey, if I'm spawning off other threads, maybe I need to load balance this. Maybe I have to keep track of how many processes these are. Maybe if I have an asynchronous thread and it was actually spawning off other asynchronous work, maybe I just need to not spawn that off, but do it in place. We had a system that was loading hundreds and hundreds of buildings, and we wound up fighting over all the cores. And so changing this around to be a little bit more efficient and understand, okay, we've run out of cores, we run out of background processes. We were able to make this thing that took 10 minutes, take 30 seconds. So do the thing on more cores. I usually call it going wide. Parallel for can break up work on an array and hand it to multiple cores. And typically we're doing this with TBB. Microsoft has a bunch of parallel algorithms as well. I'm sure there's other libraries. You can code your own with modern C++, but I like TBB and it was working well for us. You can't quite do this in a background thread. If you're building a rendering engine, very often there's a main thread and background threads, asynchronous threads, different things. So you have to be careful that you're not blowing a hole in your rendering thread because you're doing work in the background and you've gone wide. So I found that it was important to do load balancing to track how many cores are in use, and manage that. In some cases, we had a third-party application, a third-party software developers kit that was loading data, and I would pull data out of that for finding out how many threads it was running, so that our parallel 4 wouldn't wind up fighting with it. Now, if something's doing disk reading, then maybe you can have a thread that doesn't wind up counting because it's just spending its time running the disk. So you kind of have to experiment a little bit. You can have more threads running than potentially your machine has, but you very often don't want to, and also the operating system needs some space. So don't spawn too many threads. TBB has this nice ability where you can kind of specify how many. You can create, I think, a task arena, it's called. You can specify how many threads it should run, or you can kind of do it by hand. But you can limit it if you want to. So maybe you've got an asynchronous task, and you're sitting there okay, I've got 3 threads free, so I will allow this process to run on 3 threads. But just don't think that your background or asynchronous processes should instantly take up all of your cores. You're going to be in trouble because suddenly you can't draw. And I mentioned OpenMP. It's a little dangerous, but maybe someone knows more about it. But at least with those basic pragmas, it's a little tricky and might spawn more threads than you want and not play well with others. So there's a price to its simplicity. For me, I've multi-threaded a whole bunch of different systems. I find that very often there's a single-threaded phase. Sometimes I calculate offsets in memory and allocate some of those things and let everybody know, okay, you're writing your results. We did a little bit of math and figure out how much data you are going to be generating, and this is where your results should go. Now it's safe to run in the parallel 4. You got to be aware, you can't just push back inside a parallel 4. You might need a concurrent vector. Those are going to be more expensive. You have to think about, what am I doing in this parallel 4? Is it just data local, or am I touching other things? And if I'm touching other things, then I might need mutexes and more careful design. So I think it's pretty, for me, it's been pretty common to have a single-threaded phase and then a multi-thread phase. But TBB does have a bunch of concurrent data types that can help. So again, you're building this code, you need to measure. You need to make sure that things work. What you want to see is something like this, which has lots and lots of green and not a sea of red. And when you see the sea of red, there's a good chance that it's because of where you put the mutexes. You want a mutex, a critical section, whatever you want to call it, in the smallest chunk of code possible. If you put a global mutex in a system and walk away, you're probably going to wind up with a sea of red when you try to make your code multi-threaded. If 4 threads are reading and 1 thread is occasionally writing, there are writable, upgradable mutexes, which can be really useful in that kind of design pattern. Bad mutex design leads to single-threaded performance, as multiple threads just stop dead. And in Concurrency Visualizer, that looked like a red waterfall. When I started doing this performance optimization on our rendering engine, that's where I discovered, yeah, we had single-thread behavior all the time because of where our mutexes were, and nobody really knew because we didn't have a good visualization of it. And once we had the visualization of it, it was very obvious, okay, this is not great. In one case, sometimes where the mutex lives is important. So I found that I would put the mutex inside the object that was being loaded. And so, if something else needed to load that exact asset, it would block on that because we had multiple threads trying to load the same vehicle, for instance. So that was a good place for the mutex. And the bad place for the mutex was on the top level loader. So, you know, you're going to wind up needing mutexes and critical sections, but you should just think really hard about where they go. So this was an interesting test case, and one of the reasons why I don't trust Qt's concurrent system that well. So there is a different definition of mutexes from some people and others. There is a system level operating system, the OS kernel level mutex, which has a name and can be used for multi-process synchronization. I believe Qt uses that, and what I found was I had this exact same code. Just one was with the TBB mutex and one was with the Qt mutex, and you can see that they take up. I mean, this is about the same scale. The Qt code was absolutely a disaster, and I would have, again, not known without seeing this. Effectively, the amount of time it took to grab that mutex, each one it went to the kernel, and it was crazy slow. So not all mutexes are the same. Some of them are, I think, mention it here. Oh, here I explain it uses wait for single object, kernel level functionality, allows for inter-process window synchronization. TBB uses a critical section. I think more modern ones, STD mutex wraps a slim reader-writer lock, which I believe is 8 bytes, so it's better for cache coherence. You know, I'm not sure when that really matters, but I guess if you had a mutex next to some other data, you can fit in a cache line better if it's 8 bits versus 40 bytes. 8 bytes versus CS40. So there's a whole bunch of different kinds of mutexes actually, depending upon your operating system and the tools that you're using, and they're not all the same. Okay, so this was a little bit more just for my company, but I think it's true in general. Don't check in code that can't run well. It's going to be a problem eventually. You know, blowing frames can make us lose contracts, make us lose work. You should have a sense when you build a system at the get-go. How well does this run? Will it scale up? And sometimes you should ask for more time to work on it and get it right, or just build your basic data structures. You can talk with a senior engineer. Hopefully there are senior engineers. If you haven't given any thought to the system, then it needs to be redesigned, possibly by somebody like me, but you know, that keeps me employed. I always like to test with a hard case. I like to find the thing that's actually going to break the system and think about it that way, not test the easy case. I feel like that's just the right thing to do, because what's going to happen is you're going to make something with 10 lights, and then an artist is going to come by and decide to create a character or creature that is just pure made out of lights, and everything's going to fall apart. And so you just, you know, it might be an artist, it might be a new terrain, it might be a new customer. Someone's going to push on this system. And if nobody thought at all about how do I make this work better, how do I make this scale properly, you're just going to be in trouble. And at that point, it's going to be a little too late. So at the very least, you know, think about amortization, time slicing, being able to interrupt a process and come back to it the next frame. All those are really important things to at least think about. When your mutex blows up in your face, the Visual Studio has some nice parallel stacks, parallel watch window. It can be very annoying to debug multi-threaded code, or if multiple threads are actually dealing with the same exact code and you try to step through it, it's a real headache. There's this thread freeze and thaw, and I think Visual Assist has this bind thread feature also that I've played with a little bit. But what I find actually the best thing is have an option to turn off your multi-threading of the system. you know, because so this is more about this is more a thing when you're just building a system that's multi-threaded that used to be single-threaded, and something goes wrong, not with the threading, but just, hey, I need to debug this now. The best thing you can do is have a checkbox, the ability to like drop the number of threads back down so you can walk through the code sanely, because it's really painful to step through this code. There's just, I think that there are better ways. Maybe someone can have a response video and explain how they like to do it, because I find the thread freeze and thaw is a little awkward, and it only really works for like a single frame, because then you've frozen your process partly and things lock up. A couple of use cases. I talked a little bit about this earlier, the idea of culling in parallel. So, here's a spot where, this was a couple of milliseconds of work, and it turned out it could completely move onto a parallel thread. And there was a little spot where, we needed to get the answer, but it was almost always finished by the time we needed the answer. So this was a way of effectively getting culling of all of our characters for free. Right. So there were issues where like maybe it was in the same thread pool, but in general, like that wasn't really a major problem. If there was an issue where we were out of threads, one system grabbing the mutex would, it worked out okay. We weren't always loading dozens of characters, dozens of objects at the same time as trying to update thousands of characters. But this is what I was sort of getting at before. I could have sped up that cull process, and I did speed up that cull process. At one point it was a big ON search, and I changed it to an octree, and that helped tremendously, or quadtree, I think maybe. No, octree, sorry. But getting it off the main thread, it didn't matter how much I made that process faster when it was single-threaded. I could have made it 10, 20 times faster, and maybe I still could. But by moving it off the main thread, when I had spare cores, it became free. And so that's part of it. Like if your infrastructure is threaded well, some of these big O problems just become free. I can spend all of this time trying to get 10% faster on this issue, or I can just get it off my main thread, get it into an asynchronous process, and suddenly, that work that got me 10% is now getting me 100%. So this is an example of a path planner that ran an asynchronous thread that, I built this before having these tools. I imagine that it would have been so much nicer to build this kind of system with these tools available. It would have been, I just can't imagine how much easier it would have been to think about. But at the get-go, when I built this path planner, I had in the back of my mind, and it took me a couple of years to do it, where it would run in a background thread, it would time slice, and there would be sync points where we'd go and say, okay, a concurrent vector would probably do that really easily now, and I wouldn't even need these mutexes. But there'd be a mutex once a frame, just long enough to ask or get the result. And in the background, we would just run a search, run a search, run a search. Each search was given a certain number of points on the graph to sample, and so that we wouldn't run out. So we wouldn't have one pathological search stop every single character in the world from path planning. So again, this was something that I started out thinking about when I first designed the system. It took numerous iterations to actually get to that point. But at least at the beginning, I'm like, okay, what are the data structures I will need to live in the path search so that I can pause and resume this one day? And the army kept on asking for more and more characters, so and bigger terrain, so it became pretty important. So here's another system. We keep track of how many models we're trying to load. We start asynchronous tasks for each one, and we use atomics to track how many active tasks there are and paging threads there are, and try to make sure that we don't clobber and preempt the work that we're doing architecturally. Once we finish loading a model, we have to analyze it for a lot of different things, and we can do that in the background, and we can clone a copy of the skeleton of the model. So all those things we can do in the background that we had been doing in the foreground. We just sort of slowly move those pieces out, and we're able to maintain 60 hertz frame rate even when we were loading these giant models. And one problem with delaying creation of characters or models of any sort is that your API is going to have to be resilient, that if somebody wants to mess with them, you're going to have to be able to queue up those commands and play them back. And so that is the tricky part. Hopefully you manage to load the data and get it ready within a few frames, but if you can't, then you're looking at, like, you need some kind of system to sort of sync up the state that you're expecting it to be in, and deal with the fact that, like, hey, maybe someone's got a script that tried to use this object and it's not actually ready yet. So nothing's for free. I put together a particle system. In this case, I multi-threaded the update of the particle systems. So each particle system wound up in a parallel 4, and I would calculate how much memory was needed, map the GPU memory to the CPU, and then fill out that buffer in multiple threads. So, effectively, instead of sending all that data in the main thread, by mapping that data, I can fill it out in lots of different parallel threads, knowing which offset they were from that sort of single-threaded pass, and then draw everything very quickly without doing much data transfer. So it was just OpenGL, draw, 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 not send, send, send. So really, this is all just the tip of the iceberg. We go on forever. I'm sure there's lots of other videos doing deep dives on some of these topics. I did want to kind of throw out this chart talking about the different orders of magnitude from, L1, what a branch mispredict costs, when L2, how long it takes to lock and unlock a mutex, although that's probably not not the Qt mutex. But just this idea, the data-oriented design, where you're trying to squeeze more things into a cache line and pack your data more carefully. That's all really good. This gives you sort of a sense for the costs here. There was a cute Insomniac Games cache simulator at one point. I'm not quite sure its current state. I'd have to go look. So one last topic that is way too big for this talk, but intrinsics. This is an example of ray tracing in one weekend, Peter Shirley's short book. It's really fun. It has all the math for learning about ray tracing. And in this case, this is using multiple threads to do updates, but it's also using some SSE intrinsics to do the math, and it actually wound up being 4 times faster for getting the pixels onto the screen, and it really helped to work at interactive rates. So at one point there was a very simple accumulation buffer that then had to be turned into integers for sending to the video card or saving out to an image. And so this fairly simple code, the equivalent intrinsic SSE version looks something like this, and here's the commit that I did on GitHub. You can go to Gedaliah Baby Tracer and take a look. But there's lots and lots of examples of people doing the ray tracing in one weekend at different performance levels. But this wasn't this took me quite a bit more time than this did. I don't know, maybe an hour or two to get it right. It was like a 2 to 4x speed up. So, you know, if you pack your data the right way, you can use these instructions, and they do go quite a bit faster. Some processors have even larger ones that can process more data, which is very handy for doing like large-scale image processing. And you know, if you're going to do video compression, I'm sure places like Netflix are spending lots of money on those kind of systems. So that's the Intrinsics. It's really a big topic that's worth learning about, or hopefully there's 1 or 2 experts at your company that you can learn from, or send the code to and say, hey, take a look at this. You're a guru. There's also a number of libraries, as well as this Intel compiler that effectively lets you write little kernels, and it will generate intrinsic and the right kind of SSE instructions or SIMD instructions, depending upon the video card, CPU that you're targeting. So that's another way of doing this. I haven't gotten a chance to learn this infrastructure, but people say good things about it. I think Matt Farr worked on it, who did the seminal work on physically based ray tracing, physically based rendering. So that was the ISPC. So language. Okay, and ISPC stands for Implicit SPMD Program Compiler. So these are great things to learn when you are bound by the math that you are trying to do, and particle systems and the like. So thanks for listening. This was fun to do. I feel like it was kind of summarizing the last 8 years of my optimization work in terms of the way I think about certain things and apply it in a software engineering environment.